Have you ever stopped to wonder what's actually happening inside the wires that power, well, everything in your life? Today, we're going to demystify current electricity. We're starting from square one, so by the end, you'll really get how that invisible force works. Okay, so here's our game plan. We'll kick things off with what current even is, then we'll look at the force that gets it moving, the big law that governs it, what slows it down, and finally, how to make sense of it all in a real circuit. Let's just dive right in. All right, first things first, what is electric current? Before we get into anything else, we have to wrap our heads around this one core idea, the actual flow of charge. So in simple terms, it's just a way to measure how much electric charge is zipping past a certain point in a wire over a set amount of time. It's not about how fast one little electron is going, but how much total charge is moving through. It's all about the quantity. And here you can see the official textbook definition, taken straight from our source material. The net charge passing per unit time. This simple phrase, it's the bedrock for everything else we're going to talk about today. To make this way more intuitive, let's use a simple analogy that we can keep coming back to. Just picture electric current in a wire as being like water flowing through a pipe. The more gallons of water that pass by you every second, the higher the flow rate. It's the exact same idea with electrical charge. Okay, so if current is the flow of charge, that kind of begs a question, right? What's actually doing the pushing? After all, those charges aren't just going to move on their own. Well, that push has a name. It's called voltage. You'll also see it called electromotive force, or EMF for short. You can think of it as the oomph, or the energy that a source, like a battery, gives to each little bit of charge to get it moving around the circuit. And let's go back to our water pipe analogy. If current is the amount of water flowing, then voltage is the pressure that's making it flow. You crank up the water pressure, and what happens? You get more water flowing through the pipe. More voltage means more current. Simple as that. All right, so we've got our flow, that's current, and we've got our pressure, that's voltage. Now this brings us to a really fundamental rule that connects them, along with one other super crucial piece of the puzzle. So yeah, how do these three things all fit together? Answering this question leads us to what is maybe one of the most powerful and fundamental relationships in all of electricity. And that relationship is defined by this beautifully simple equation. This is Ohm's law. V equals I times R. Looks simple, but it's incredibly powerful. So let's break down exactly what each of these letters represents. Here's the whole shebang. V is for voltage, our pressure, and it's measured in volts. I is for current, our flow, measured in amperes, or just amps. And the new player here is R, for resistance. This is the obstruction that slows down the flow, and we measure it in ohms. So what Ohm's law is really telling us is that for a set amount of obstruction, if you push harder, more voltage, you're going to get more flow, more current. Let's put some real numbers to this to make it concrete. Let's say you have a 12-volt battery. That's our V. You connect it to a circuit that has 4 ohms of resistance. That's our R. If we just shuffle Ohm's law around a little bit to solve for current, we get I equals V divided by R. So you take 12 volts, divide by 4 ohms, and you get a current flow of 3 amperes. See? Easy. So we've been calling resistance the obstruction. But what actually determines how much resistance a material has? I mean, why is a copper wire so different from the lead in your pencil? What's going on there? Well, our source material gives us the answer right here in this formula. Now, don't let the Greek letters scare you off. It might look a little complicated, but it's really just telling us that a material's resistance boils down to 3 really simple physical properties. Let's break them down. First up, we've got length, the little L. The longer the wire, the more of an obstacle course the charges have to run, so the resistance goes up. Makes sense. Second, cross-sectional area, or A. That's just how thick the wire is. A thicker wire gives the charge more room to move, so the resistance actually goes down. And finally, this little rho symbol stands for resistivity. This is just a built-in property of the material itself. It's a measure of how much that specific substance naturally fights the flow of current. And this idea of resistivity is why we have different classes of materials. You've got conductors, like metals, which have super low resistivity. They barely put up a fight. That's why your charging cable is made of copper. Then you've got the total opposite, insulators, like glass or rubber. Their resistivity is huge, stopping the flow completely, which, is great for keeping you safe. And right there in the middle, you have these amazing materials called semiconductors. They're the magic ingredient in every computer chip because they let us control the flow of electricity with incredible precision. So, Ohm's law is awesome for simple single-loop circuits. But what happens when things get more complicated? With multiple loops and branches and wires going everywhere? For that kind of messy, real-world circuit, Ohm's law alone isn't going to cut it. We need a more powerful toolkit. And that's where Kirchhoff's rules come in. There are two of them, and they are essential. First is the junction rule. All this says is that at any point where wires meet, the total amount of current flowing in has to equal the total amount flowing out. You can't just lose charge. It's basically conservation of charge. The second one is the loop rule. This rule says that if you travel in any complete circle in a circuit, all the voltage gains and drops have to add up to zero. This one's all about the conservation of energy. Phew! Okay, we have covered a lot of ground. So let's just take a second and wrap everything up with a quick cheat sheet of all the key terms and formulas we've just gone over. Now, this is really useful. This table, pulled straight from our source material, is a fantastic summary. It lays out every single quantity we've talked about, from current to resistivity, along with its official symbol and the unit it's measured in. This is a perfect reference to have handy. And finally, here are the core formulas to remember. You've got our old friend Ohm's law, V equals I times R. You've got the equation for calculating resistance based on a material's properties. There's a formula for current density, and of course, Kirchhoff's junction rule. These four equations are really the mathematical heart of everything we've talked about today. So I'll just leave you with this question to think about. Now that you understand these rules of flow, where can you actually see this stuff at work in your daily life? I mean, think about the heat coming off your laptop charger. That's literally resistance in action, turning electrical energy into heat. Or think about how a dimmer switch works. These principles are absolutely everywhere, silently powering our world. So thanks for watching and keep exploring.